In this lecture, let us talk about adaptive delta modulator. In short, we call ADM. As I said, in delta modulator, there are certain issues, right? Like slope overload problem and granular noise problem. Okay, so those two are eliminated with the help of adaptive delta modulator. So the idea is extremely simple. So the step size is no longer kept fixed. Okay, in delta modulator, the step size is fixed. Okay, and step size is fixed and the width also fixed. Okay, so sampling interval TS also fixed. But in adaptive delta modulator, the step size is no longer fixed. Okay. Therefore, whenever slope overload distortion occurs, then what you do is you increase the step size, and whenever the granular noise occurs, then you reduce the step size. Therefore, adaptively you change the step size in order to remove these two problems. Okay, so it is the step size is made to vary according to the incoming message signal. Okay, so the step size is made to adapt with the ADAPT, okay, adapt with the nature of the signal, right? If step size delta naught is small, when M of is small, when M of t is nearly constant. Okay, that means slowly varying signal. Nearly constant means what? It has small variations. Okay, that means M of t has small variations. So in that situation, what you do? You reduce the step size, right? It is made larger. Delta is larger if M of t is rapidly changing or very fastly changing. In that case, what you do? Increasing step size. So this is one possible way by which you can overcome these two drawbacks. Therefore, delta step size made small when M of t has small variations okay, and delta naught step size is made large if M of t changing rapidly. So this is the whole idea of adaptive delta modulator. Okay, let me draw the diagram. So you have M of t message signal, give it to the comparator, same diagram, and then this is given to the limiter, hard limiter. So the limiter looks like this. I explained the limiter operation, and then output of this comparator is denoted by d of t, different signal, and the output of limiter is capital del of t, and this is multiplied by the impulse train. So here you have pulse generator. It generates a train of pulses, and finally you will get the output x suffix c of t. So at the output you will get either positive impulse or negative impulse, that's all. Okay, with amplitude +1 or -1. So the output is binary in nature. Now from the output take the portion and you put the integrated same circuit, okay, with small variation. Now before that, as I said, you should increase the step size or decrease the step size depending upon the message signal, nature of the message signal. Therefore, instead of giving constant feedback like this, I'll put a variable gain amplifier here. Okay, instead of giving directly to the integrator, I'm going to feed the integrator through a variable gain amplifier. So I'll put an amplifier, but its gain is variable in nature. So when I say variable, then I should give some other control voltage. See, everything is just about the same as it was earlier with the delta modulator. There is a small difference, and the difference is I have introduced here. What I have introduced here is a variable gain amplifier in the feedback path. Okay, so this is the feedback path. In the feedback path, I have introduced a variable gain amplifier. Everything else is the same. The variable gain amplifier is an addition in the system. Now you can ask me a question, what does this variable gain amplifier do? Right? The variable gain amplifier changes the impulse strength that is going to the integrator. See, the impulse strength is going to the integrator, and it changes the strength of the impulse. That means increase the step size or decrease the step size. So how do you do that? By multiplying the impulse by gain. Okay, here impulse is coming, and that impulse is multiplied by variable gain, and therefore it is able to change the step size. See, here you have the train of, see, this kind of pulses is given to the variable gain amplifier. And if you change the gain of the amplifier, then what will happen? The pulse train either increases, the pulse strength either increases or decreases. That means essentially indirectly you are controlling the step size. Okay, therefore it is able to change the step size after integration. So here, if you look at here, the step size will be changed. Now, since it is a variable gain amplifier, then the gain should be controlled somehow by an electrical voltage, external voltage. Someone has to come and control the gain of the amplifier. Okay, for that what I am going to do is, I will take the same signal, give it to the low pass filter. I will explain why this low pass filter and square law device or something else. Let me, 1 second, the space is not sufficient. 1 minute. Okay, now let me take the output here. Okay, here I'll put a square law or modulus device. I'll explain why the square law and modulus device with an example so that we can easily understand. And low pass filter. Okay, like this. Okay, now let us understand this. And what is this? This is the controlling signal, okay, which is going into the variable gain amplifier. So this guy is going to control the gain of the amplifier, right? So this guy controls this control signal will decide whether the gain is large or small. So the output of the square law or modulus device will decide the gain of the amplifier. When the gain is large, the step size will be large. When the gain is small, then the step size will be small. Therefore, gain is large, then step size will be increased. If the gain is small, then the step size delta will be decreased. And what we would like to do is that the gain should be large when rapid changes are taking place. Whenever you have a signal like this, then so it cannot follow the rapid changes. In that case, you have to increase the gain like this, right? Again, the gain should be small when the slow variations like this. When there are some slow variations, then this step size should be as small as possible, right? So to understand, let us look at this two picture that we have seen earlier. Okay, now let me consider a slowly varying signal like this. Okay, okay, this is a situation where the variations are very small. Now what is a delta modulator output is going to be in this? It goes like this, comes back, then again goes back, comes back, keep on oscillates between positive pulse and negative pulse. Now in this instant there is a positive pulse, and in this instant there is a negative pulse, and here again it increases positive pulse, and here it is negative pulse, positive pulse, negative pulse, positive pulse, negative pulse, positive pulse, negative pulse. So this is the output of your delta modulator. Okay, so this is your x suffix c of t, train of pulses. So alternatively it is keep on changing, 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1, plus 1, minus 1, and so on and so forth. Now if you give this guy to the low pass filter, what will happen? Low pass filter is essentially an some kind of an integrator, right? You have a sequence of positive and negative impulses, right? For this kind of situation, we are going to have a sequence of positive and negative impulses, one after another. Alternate impulses are going to be of different polarity. Different polarity. So when we are undergoing a small variation, and if we have a large step size, this is what is likely to happen. And what we like to do is, in this situation, reduce the step size, right? If it keep on changing like that, then our motto is reduce the step size. So when the delta modulator finds this situation happening, that is alternate impulses are positive and negative, you can interpret it to mean that the existing step size is too large. Therefore, you must reduce it. Okay, so therefore the step size is being controlled by the variable gain amplifier, variable gain amplifier. Okay, where is the figure? It's here. Okay, so the step size generally like a fixed amplitude, but I need to change it somehow. They have to be change it. See, in this figure these are fixed one, either plus 1 or minus 1. There is no change in this output of your modulator. Okay, output of modulator, no change in its strength, either plus 1 or minus 1. Okay, there is no change in the output, but I need to change the step size in the feedback path. How can I do that? So that is a question. Okay, so the output of your delta modulator is of fixed amplitude. They have to be fixed amplitude because we can only allow two levels, either plus 1 or minus 1. Therefore, the output of your delta modulator must be only binary valued, either plus 1 or minus 1. We cannot have variable values at the output of the delta modulator. Okay, so therefore I have a provision for changing the impulse strength in the feedback path. Okay, therefore the whole idea of adaptive delta modulator is, or delta modulation for that matter, is that indirectly we need to increase the step size. Okay, so we need to somehow find out a very simple mechanism which is sensitive to the nature of the signal. Okay, incidentally this is obviously not the unique implementation. Okay, so this implementation is not the unique implementation. There are many possible variations of this implementation, and you can find one and you can use it. Okay, we'll try to understand this now. So alternatively, it is positive and negative. So in this situation, what you do is give it to the low pass filter, right? So the delta modulator produces an alternate sequences of positive and negative impulses, and this system will interpret it to mean that the step size that as it exists is too large. When will you get this positive and negative impulses? When the step size is too large. Therefore, it must be made small. How will you do that? Just pass it through the low pass filter. Okay, so whenever you get this alternate positive and negative impulses, then the system understands that the step size has to be reduced. So if you give to the low pass filter will produce an output. What will be the output of the low pass filter in this case? It will be nearly a zero value, 0 volt. Okay, very low value it will produce. Okay, so whenever you have a sequence of positive and negative impulses, it produces a nearly zero kind of values. Okay, it produces nearly 0 voltage, or I can say 0.001 voltage. Very low voltage it will produces. So look at the figure. Whenever the output contains sequence of positive and negative impulses, then the low pass filter output will be very, very small. Nearly low voltage produces. And that low value will be squared here, square law devices. Square and square root is taken here. Therefore, what about this point? This also very low. If the controlling signal is very low, then this gain of the system is the gain or the amplifier produces the gain to the incoming pulse will be low. Therefore, the step size is decreased. See, whenever you have this kind of impulse train, the low pass filter produces very, very small value, close to 0 voltage, and that voltage is taken modulus here, square law device, I mean square of that value, that's it. And output is given to variable gain amplifier. Now this controlling voltage is very, very small. That means the amplifier gives very low gain. The amplifier provides very low gain. That means the step size is reduced. And if the step size is reduced, then that is given to the integrator and our old friend. Okay, so that's it. So the step size is reduced, and it follows the slowly varying signal. So that's how this granular noise is reduced. Okay. Now, so generally at the output it is looking at 4 or 5 or 6 impulses, and you are looking at the average value. Okay. Here this low pass filter will look at 4 or 5, 6 impulses which are alternately changing. Therefore, the output of low pass filter will be very, very small, and the output of modulus device also less, and that is nothing but a gain, controlling voltage. If the controlling voltage is less, the gain also reduces and step size is reduced. Okay. Now, on the other hand, let me explain here, then I'll come back to this figure. On the other hand, I have the signal like this. It goes very fastly. Okay, so if you have a slope overload situation of this kind, it goes like this, keep on goes. Then what will happen in this case? Here I have positive impulses, here positive impulse, positive impulse, positive impulse, positive impulses, like this. A train of positive impulses, a long sequence of positive impulses. So whenever you have a long sequence of positive impulse, then you must understand that there is a situation where slope overload distortion occurs. So if you give this kind of thing to your low pass filter, what will happen? It gives large value in the output. Okay, so the value will be like this. So this is the output of your it keep on increases. Your low pass filter will increase like this. So in that case, the low pass filter average value low pass filter average value output will be large in magnitude. Okay, so whenever you have sequence of positive impulses, the output will be large. Go to the figure. So if you have this sequence of pulses like this, then in this point you will get large value, large average value. So, and that is again given to the modulus device, and here also you will get large value. If the controlling signal is large, then the gain offered by the amplifier is increased. If that is increased, then step size is increased. If step size is increased, the output of the integrator also high. Therefore, the slope overload distortion is eliminated. So this is one way. On the other hand, I have a signal like this. Like this. So now my delta modulator will follow like this. Then it goes like this. It cannot reach the signal. So here also what happens? So here you have positive impulse, negative impulse, positive impulse, negative impulse, then let's say negative, and here also negative, 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 like this. Now look at here, you have train of negative impulse, all are negative. In that case, what will happen? Again, the output of the low pass filter in this region, it gives large negative value. Okay, so it gives a large negative value. I mean it gives. So therefore the output of the low pass filter will goes like this, and if you take the average, it will be large value. This is T, and VLPF of T, low pass filter output. Okay, so go back to this figure. So whenever you have negative impulses like this, then also the low pass filter produces large value, but in the negative direction. But again you put a modulus device, right? So that negative will be converted into positive value. That is the reason we put a square law device or modulus device. Again it is converted into positive value, large positive value, and that large positive value is given to the integrator. Where is the integrator? Oh my god, I forgot. Yeah, it is here. Okay, it is here. Okay, so it provides large value, and that large controlling signal is given to the amplifier. So therefore the gain is increased. If the gain is increased, the impulse strength is increased. Therefore the integrator output also increased, and the slope overload distortion is avoided. Therefore in that case, the low pass filter average value output will be large in magnitude. Okay, but of course it could have any sign, positive or negative. If you have continuously positive impulses, then the output of the low pass filter will be positive. If you have continuously negative impulses, the output of the low pass filter will be negative. But the gain should be 0, right? So the the controlling voltage should be positive. So that is why we put a square law device in between the variable gain amplifier and low pass filter. So and that's the reason immediately followed by the low pass filter, we have a square law device or a modulus device. Okay, because I am not interested in to know whether the difference or error is large positive or large negative. Ultimately what we need is, we need a controlling voltage to control the gain of the variable gain amplifier. Okay, if the error is large, therefore I must increase the step size. That means the slope overload exists, so I must increase the step size. Okay, so therefore the control signal becomes large and the variable gain amplifier gain is increased. So step size is increased, and that is a basic principle of adaptive delta modulation. Okay, if there is an alternating how will you reduce the step size? Because I mean the low pass filter is giving a DC value, so that DC value is very low value. Okay, I mean it's very small value. Okay, the small DC signal results a small value of the gain. because it is controlling the gain of the variable gain amplifier. Okay, and the manner of controlling the gain is that when the control signal is small, the gain is very small. When the control signal is large, this is my control signal. If the control signal is small, the gain is small. The gain is very small. Okay, when the control signal is large, the gain is very large. Even if there is small control signal, then small, very small, gain. That's all. Okay, small control signal, very small gain. Large control signal, very large gain. That's all. So this is this control signal is controlling the gain of the amplifier. Okay, after all, we need some parameter to indicate whether the slope overload kind of condition exists or the granular kind of condition exists. Based on that, we have to take action in the form of changing the gain of the amplifier appropriately, and that indication is coming to you through this control signal. Okay, as far as the receiver is concerned, how will you do that? Very simple. Okay, so same, you take this signal and again give it to variable variable gain amplifier VGA, and then you put an integrator, and here same signal. Okay, you put a low pass filter and you put a square law device, and this is given to here. That's it. And this is your approximated signal M cap of t. That's all. Okay, so the demodulator is very simple. So whenever you find a sequence of positive impulses, then you have to reduce the gain. Whenever you find the same polarity pulses, then you have to increase the gain. Whenever you find alternate +1 and -1, you have to decrease the gain. So that is controlled here. So this is nothing but your demodulator. So it's a very simple implementation. In fact, after the integrator, if you want, you can put one more low pass filter to smoothen out the output. That's it. Okay, so that's all about the basic principles of adaptive delta modulation. Okay, let me stop at this point. Thank you.